Hello everyone, it's Benny, and in this video, what we're going to be doing is we're going to be looking at the idea of transformation. That's the ability to take the triangles we have right now and scale them up and down, zoom in and out on them, rotate them all about the place, even move them just left to right or something. You know, it's the ability to take the triangles and move them around in 3D. And to start with this, I'm going to give you a little bit of background. So, right now, we have vertices. And granted, these ones are pretty fancy vertices. They got texture coordinates with them. They've got, well, we're filling them in, so we got a filled triangle. And we're even drawing a brick texture on them. So yeah, these are some pretty fancy vertices. But at the end of the day, they're just vertices. And so, what we want to do is we want to take these vertices and put them in some new position on the screen. And you can use whatever function you want as an example. Maybe it's just moving them to the left or something. But you know, at the end of the day, we're just moving around. How can we go about doing this? How can we take these vertices, take this triangle, and draw it in a new position? Well, if you look at the code we've done so far, you might think, ooh, I know. When we've got our mesh, we've got this function called GL buffer data. And what this lets us do is it lets us take some vertex data and send it to the GPU. So what you could do is you could take the vertices that we have right now, calculate their new positions, and use GL buffer data to send that to the GPU. Then all you have to do is use the draw function in the mesh, and what do you know? You're drawing the triangle in its new position. And you can do that, and that works. And in fact, for a very long time, that was the way to do things. That's how games, all the way up to even the late 90s and early 2000s, that's how they did things. But, well, let's look at how that actually works. So, we start with all our vertices, and we got these in the CPU, in memory somewhere. We want to move them around. So I'm going to load the first vertex, and BAM! I'm going to do some math magic. Going to do some logarithms, exponential functions, plus, minus, whatever it takes. You know, whatever I'm doing to get the vertex in its new position. Alright, cool. We got one vertex, it's in its new position. Now what? Well, it's great, but we got some more vertices. So let's take the next vertex. Gonna do it, and BAM! Perform all the math magic. Exponentials, logarithms, whatever it takes. Whatever gets it in its new position. That's great. But that's still not all the vertices. Let's do it again. Take that final vertex, and BAM! Do the math magic. Exponentials, logarithms, whatever it is, and finally get that in that last position. And you keep on doing this over and over for however many vertices you have, until finally you've got every single vertex all gone through the math magic, all in its final transformed position. And what do you do now? Well, you know, you're just going to use the GL buffer data, send it all to its new position, draw it, and finally, you've got your triangle, except slightly to the left. Yeah, I know. It's kind of anticlimactic, but there's a good reason for that. You might have sort of caught on, this doesn't really scale well. If I have really complex geometry, this method, well, it's not so nice to do math magic 100,000 times, or, you know, just to move something to the left. So, this is great, it works, and you can do some pretty cool stuff with it. But let's take a step back, and let's see if we can do this a little bit smarter. So, let's take a step back, and let's try this again. We have our vertices, and what we want to do is we want to take these vertices and transform them somehow, move them around in 3D so that they end up in some new place on the screen. And as it turns out, there's a few tricks to this that we can leverage to make this not have to go through this big, gigantic, serial process of math magic. For one, if we are going to be performing some transformation on these vertices, chances are we're going to want to do the same transformation for every single vertex. You know, unless our mesh is like some human model and we want it to be waving its hand or something like that, there's a pretty good chance we're going to not want to do something like, oh, I want to move this vertex to the left, but this one is going to just stay put or something. You know, no. We're probably going to want to move every single vertex around in the same way. And there's another trick we can leverage. Because one interesting sort of mathematical property of transformations is that no matter what ridiculously complex transformation you want to apply, you can represent it with a matrix. So, that's right, viewers, the matrix has you, and it is going to make our triangle transformations ridiculously fast. I would like to say, though, the idea of using matrices to make transformations simpler like that is not new. This has actually been done even back in the 90s when they're doing this math magic over and over again. Usually the math magic would be a matrix. So, if you ever played an old game like Quake or Unreal or something, now you know how they're moving everything around on the screen. But the thing is, we have something that Quake and Unreal didn't. And that is the GPU. Specifically, the Vertex Shader. You see, what's our Vertex Shader doing? It's taking some input set of data and then transforming it into a relevant piece of information for the GPU to draw. So we can take advantage of this. Rather than just spitting everything out like normal or converting whatever internal format we have into the GPU position, we can just pop a matrix in here, have that matrix representing the transform we want to apply to our mesh, and apply that to every single vertex that goes in here. The advantage to this, we don't have to go through a big, gigantic serial process, because this is being done mostly in parallel. If you have, like, a really huge set of vertices, like 2 million vertices or something, then yeah, it's going to be doing it in serial to some extent, but not nearly the extent that if you would do if you're doing it with just uploading it with GL buffer data or something. And furthermore, there's very little cost to this, because the Vertex Shader is something that's going to be done anyways. We're already performing some transformation. I mean, you're already going to be doing some transformation on it, so why not take advantage of it? Why not add in a matrix? That's not to say the matrix in and of itself is free. Adding on the matrix does have some cost, but again, it's not that much. So, yeah, this is the trick. All you have to do, construct a matrix of your transformation and send it to the Vertex Shader. And because this is in parallel, and because of the step that would be done as part of the GPU process anyways, the transformation comes at very, very little cost. So you don't have to do a giant serial process like before. And also, it's a lot nicer to just say, okay, send the vertices through the Vertex Shader, and then everything just comes out in the right position. And there. There's also a lot of other advantages to doing this way. Like, for example, we can draw the same mesh in a whole bunch of different positions, orientations, and sizes without changing the mesh data. All we'd have to do is draw it again with a different matrix. But I'll talk about those later. That's getting a little bit ahead of ourselves. Right now, let's just focus on getting a matrix that's relevant for transforming and moving our vertices around with the Vertex Shader. Okay, so now it's time to dive into the code and take our matrix idea into a reality by means of the transform class, which I already made this header file and set this up off screen because I think you're pretty used to the way I like to set up my classes by this point. Now, here's the thing. People don't intuitively think of movement in terms of matrices, at least not most people. Now, I don't know about you, but I think of objects as moving left and right, not as moving with a 4x4 matrix with the fourth column vector is positive versus a 4x4 column matrix with the fourth column vector is negative. My word, that's a mouthful. You see what I mean? You know, people don't tend to think like that. So that's the purpose of this transform class. It's to give us a nice interface for moving, rotating, scaling, just generally transforming our object and moving it around in 3D in an intuitive way. And then ultimately giving it a nice convenience function to convert that into a matrix when we actually need to draw it. And that's the purpose of this. So, unsurprisingly, we're going to be highly leveraging GLM's, GLM, all its vector and matrix functions. So I'm going to just go ahead and include glm.hpp, and let's get started with the constructor. Now, since this is going to be a relatively simple class, in fact, you could probably just make this a struct. I'm just making it a class because I'm paranoid, but, it's because this is going to be relatively simple, I'm just going to make this a nice header-only file. And so, this is going to take in Well, I'm going to have three different ways we can transform our object. We can either position, we can move it around, we can put it in some place in 3D. We have rotation, which will control its orientation, rotate around in various ways. And a scale, which will let us control how big it is. Now I'm going to have so I'm going to create a vector for all three of those, because that seems to be the most intuitive way to think of them. So I'm going to have const glm vec3. It's going to be a reference. I'm going to call it pos. I'm going to have some other const glm vec3 reference, call it rot for rotation. And a final const glm vec3 reference I'll call scale. And that's what our constructor is going to take in. Now, I'm going to make the actual data for position, rotation, and scale, because it's going to store the vector. I'm not going to actually store the matrix, because it's easier to, manipulate vectors and just calculate the matrix when it's needed. So, well, sort of ran through that, but there you go. If not, if you don't get it now, you'll see the idea. But because of that, I'm just going to make the actual data in the transform class vectors. So, and have one vector for all of these: position, rotation, and scale. And you know what? Why not? I'll try an initialization list this time. You can initialize things really either way, and it's not going to matter too much in the end. But why not? Let's do it this way this time. So, oh, I almost forgot. Because these are member variables, we'll make sure to prefix them with an M, at least if you're following my conventions. So, yeah. Impos is going to be pos. Imrot is just going to copy the rot. And imscale is just going to copy the scale we pass in. And for convenience, I'm going to go ahead and specify defaults for these. Positions is going to default to vec3 with nothing. Rotation is just going to default with a vec3 of nothing. And scale is not going to default to a vector 3 of nothing, because then, what's the scale going to be? It's going to be 0. What's an object of size 0? Well, it's nothing. We're not going to see anything. So yeah, my scale is going to default to 1.0, 1.0, and 1.0. And there. And, well yeah, there you go. And I'm going to go ahead and create getters and setters for this. And I went ahead and created the getters and setters off-screen, because there's really nothing that interesting about them. The only thing I think that's really worth mentioning is, in my getters, I am returning by reference, and that's really just a convenience thing, so I don't have to say get the position and then add something that I want to change it by and then set it again. So yeah, that's really the only thing worth mentioning there. So now let's get into the real meat of the transform class, where we take our position, rotation, and scale and convert it into a matrix. So this is going to be an inline function. It's going to return a glm mat4, which is a 4x4 matrix, and this is going to be called getModel. The reason I'm calling it that is because in OpenGL lingo, a matrix that contains the position, rotation, and scale of something is generally called the model matrix. Sometimes it's called the world matrix, depending on where you're reading it from, but they're all the same thing. Don't let it fool you. And finally, this function is going to be const, because this isn't going to be changing position, rotation, or scale. And there. Now, interestingly enough, glm does not include the transformation functions when you include glm.hpp. So I want one more include. This is going to include glm/gtx/transform.hpp. And this will include all the transformation functions. Now here's the way I'm going to set this up. glm has a few functions for just converting basic position, rotation, and scale into into 4x4 matrices. For example, I can have a glm mat4, let's call it pos matrix, and I can initialize this to glm translate with mpos. And this generates a 4x4 matrix with the position. And I can do the same sort of thing for scale. So for example, I can have a matrix called scale matrix, which has, not just translate, excuse me, glm scale with mscale. And yeah, it just provides a whole bunch of nice convenience functions for converting basic position, rotation, and scale and stuff into matrices. For rotation, however, things get a little bit interesting. You see, the thing is, the way we're representing our rotation right here is the way you'd sort of intuitively think of rotation. We have some angle rotation around the x-axis, some angle rotation around the y-axis, some angle rotation around the z-axis. This is generally not a recommended way of representing rotation, because this can run into an issue called gimbal lock, where some rotations actually end up not being possible from certain orientations, and it can be kind of nasty. I'm not going to talk about it too much in this video, but yeah, that is a limitation of representing it in the nice, convenient way. If you're really serious about representing rotations, I'd recommend doing it in quaternions, where it's not internally represented like this, but conceptually it's representing some axis with a vector, and then some angle of rotation around that axis. The representation is not exactly like this, and I'm pretty sure GLM has some function that lets you convert from that intuitive angle axis representation to a quaternion. But yeah, that's the way I would recommend representing rotations, because it doesn't run into any of those issues, and it has a few other nice features, like you can interpolate between rotations easily. But anyways, that's another topic for another time. I think it's important to bring up that limitation. And partly because of this, GLM does not have a nice convenient function for converting our basic different angle rotations to a matrix. So we're going to have to do this the sort of old-fashioned way. Rotation X matrix is going to equal GLM rotate. And this takes some angle and some axis. So for my angle, this is going to equal mrot.x, which is the rotation around the x-axis, which of course would make sense for the matrix that's supposed to represent the rotation around the x-axis. And then I'm just going to pass in a GLM vec3 of 1, 0, 0 to represent the x-axis. And that's how I'm going to do this. So yeah, this is how I'm going to initialize all of the different matrices. Rotation x, rotation y, and rotation z are going to be similar. They're going to take mrot.x, y, and z, and like this. And what do you know? Now we have one matrix for rotation around x, my, and z. And there. So now we have 5 different matrices, each representing a slightly different part of our overall transformation. How on earth can we possibly combine them? One of the nice properties of matrices is that you can actually combine them simply by multiplying them. The downside to this is that it's not commutative, meaning, for example, if I multiply a position matrix by the scale matrix, that is not the same as multiplying the scale matrix by the position matrix. It'll actually do something slightly different. I'll talk more about that in a moment, but yeah, order matters in this case. And this is none the more true for our rotation, where we're going to end up with a slightly different rotation depending on the order where we combine our different rotation around the different axes. I'm going to do it in the basic XYZ manner. You can do it, again, however you want. So I'll say gmat4, I'm going to call it just rot matrix, and that's going to equal rot z matrix times rotation y matrix times rotation x matrix. Because of the way the matrices or matrix multiplication is evaluated, you're actually going to want to write out the multiplication in the reverse order you intended. This code right here is actually going to apply the x, y, and z matrix in that order. So yeah, don't let this fool you. I know it's kind of tricky because it is non-commutative and you have to write it backwards, so yeah, it gets a little nasty like that. But yeah, don't let it fool you. You want to write the matrices out in the opposite order you want them applied. And finally, with that, we can return our final matrix. And the way I'm going to do this is I'm going to apply scale first, then rotation, then the translation, or the position matrix. So I'm going to write them out in the opposite order. Position, then matrix times rotation matrix, times scale matrix. And you want to be careful with this, because you get different results depending on how you do this. For instance, if I do, say, I don't know, position first, then the object's going to move way out. Then once I do rotation, the object's going to sort of orbit around the center of the world rather than, well, actually spinning like you might intend. So yeah, you can get different effects depending on how you want to apply the matrix multiplication order, but I find this is the most generally useful way, because first it gets it to the appropriate size, then it will rotate the object so it spins around, and then finally it'll move it into its position in the world, which is generally what you're looking for. And with that, that's really all there is to converting our transformation into a matrix. So our next step is to actually get this matrix and send it to our Vertex Shader so that, well, we can actually move things around with our big fancy matrix representation. Okay, so we're back in GLSL, in our Vertex Shader. And what we're going to do here is we're going to take in a matrix, and then we're going to transform our position by it to, actually implement this whole matrix transformation in the Vertex Shader idea. And our first step in this is actually getting the matrix into the Vertex Shader. Now, we already talked about this very briefly in the Fragment Shader, but GLSL has a special type of variable called a uniform variable. And what a uniform variable is it's a variable that can be set by the CPU. So if I have, say, a uniform mat4 that I call transform, what I can do is I can save some matrix, some 4x4 matrix, to this uniform in my actual program. And then, well, that will be set to, say, whatever matrix the get model in the transform returns. And then I can just apply that matrix to every single position. So it's really that simple. And in fact, the application is pretty simple too. All I have to do is say transform times the vec4 position, and that'll apply the transformation. One interesting thing to note here is this 1, because believe it or not, this actually has a pretty significant impact here. Just by the nature of the way that the transform matrix is storing the translation part of it, moving things around, you can control if and how much of that translation is actually applied to the position. If it says set this to 0, then no translation is performed. Then this will only do rotation. So, yeah, I can just completely cancel out any translation in the matrix just by setting this to 0. If I set this to 1, it'll apply like normally. I can have twice as much translation by setting this to 2. I can have half as much translation by setting this to 0.5, and etc., etc. So, it's just a little neat thing you can play around with if you like to. And you can do some interesting things like that, which we'll actually cover in video 7, but, I just thought I'd bring it up here. Just something you can play it with after the video is done. And there. And honestly, that's all you need to do in GLSL. With this will take whatever matrix we have set here, and it'll apply it to our position, to get our final position that we're going to, for the triangle. And that's it. It's that easy. The final thing we need to do here is we need to update our shader so that it actually saves a matrix into the transform uniform. So I'm going to do a few things here to make our lives a little bit easier when we add more uniforms in the future. And the main thing for this is I'm going to have an enumeration. It's going to have, well, just numbers that'll help us refer to our different uniforms. For example, I have one uniform, I'll call it transform U, and then I'll have something at the end of this called num uniform, so I know how big our uniforms list is, and there. There's just an enumeration to help us refer to it. Kind of like we did in, in Mesh with the enumeration for vertex buffers, except this one's going to be for uniforms. And, whoops. And also, like we had in transform, I'm going to have an array of GLUint for the uniforms, if I spell it right, and it's going to have the size of the total number of uniforms. Like just about everything else in OpenGL, we can refer to the actual uniform variables with a handle, which is, guess what, a GLUint. So that's the purpose of this. So now that we're in Shader, we're actually going to have to figure out where the GPU is storing these different uniforms that we want. So I'm going to access our m_uniforms array, if I, again, spell it right. So m_uniform sub transform u, so at the location of our transform uniform, this is going to be equal to something. We need some OpenGL function that lets us figure out what handle refers to our transform uniform. And OpenGL provides a nice function for this, called glGetUniform. Did I spell it right? GL, okay, I guess IntelliSense just doesn't want to work. glGetUniform location. And this takes in two parameters. The first parameter is the program we want to get the uniform from, so that's going to be mProgram, our shader program. And the second is the name of the uniform, and we call the variable transform. So there. Now we have access to the transform uniform. It's just that easy. So, honestly, that's almost all there is to it. Now that we have a way to refer to it, the final thing we need to do is actually set it to some transform. So I'll have a void update function in our shader. And what this is going to do is it's going to update all the uniforms in our array to some new set of values. In this case, it's just going to be the transform, but in theory, this could expand to more things later on. Here, I'm going to take in a const transform reference. I'll call it transform. And it's that simple. So, now that I got the function, I'm going to go right under bind. It's going to be void shader : update. Don't forget that or you'll run into issues. And now all we have to do is actually update it. OpenGL provides a function to update the uniform, surprisingly. And this one's called GL uniform. And has a whole bunch of different functions to update different types of uniforms. I'm actually looking for the uniform matrix function, uniform matrix 4, FV, and it's called 4F, for matrix 4 of floating point values, which is the type of value that GLM is storing when in its matrix. So that's why we want that. And this only takes in a few parameters. The first parameter is the actual uniform we want to update. So this is going to be our mUniform sub transform U. So, well, which is going to be the handle to the uniform with our transform in it. The next is how many things we're sending here, just one. So, I'm going to pass in a 1. The next parameter is a little bit interesting. This is whether or not we want to transpose our matrix. Because depending on how you set up the matrix, you might actually have a perfectly valid matrix, but just need to transpose it to be in the order OpenGL expects. GLM already has it in the proper order, so I can just pass in GL false. We don't need to transpose it. But if you're writing your own matrix classes, and for some reason the matrix isn't updating right, even though you're sure all your matrix math is right, this might be your issue. You might just need to transpose it because it's not quite in the memory arrangement OpenGL is expecting. And final variable is the actual data. So here's how I'm going to do this. Before I call the function, I'm going to have a glm mat4. I'll call it model, because that's what it is, the model matrix. And it's going to be equal to transform.getModel. And I'm just going to pass in the address of model sub 0, 0, 0, accessed like an array, which should give me the address of the matrix, because it's giving me the address of the first element. And, well, really, that's all there is to it. With that, all we should have to do is call update in the shader, and as long as we pass in a valid transform, it should set our uniform to our matrix, and then when we draw our mesh after that, all the different vertices should be able to be put in their nice final transform position really easily. It's cheap to update because we only have to just send one matrix to the GPU. It's cheap to perform because it's very little extra overhead to the vertex processing. And best of all, in my opinion, it doesn't matter how many vertices we're doing this with. All we have to do is have one matrix, and it'll be perfectly valid for every single vertex, whether we have 3 or 100,000 of them. So, yeah, let's go ahead and let's put this into practice. In my main file, I'm going to include transform.h. And I'm going to create a transform right below my texture. I'm going to call it transform. I'm going to call it transform because I'm not very creative with my names. It's going to take in some position. You know what? Let's just not specify anything yet. Let's just have a transform just with the default, just to make sure our defaults are working. So right now, once I update this should do nothing. Yeah, kind of a boring example, but don't worry, it'll be more interesting in a moment. So I'm going to say shader.update with transform. So that should take that transform and send the matrix to GLSL, so that once we actually draw the mesh, actually let's put this below the texture.bind just because I prefer it that way for some, I don't know which way I prefer it. I'll put it this way for now. But yeah, it's going to update this so that when we draw the mesh, all the vertices will be multiplied by that matrix, and there. So let's build, Control F9, let's see what errors we get. Alright, transform does not name a type because I didn't include transform in shader.h. That's okay, I can just include transform.h here. And that should be okay, so let's build again. And now, include, oh, and forgot closing thing. And there, so now let's see what happens. Okay, cool. We didn't break anything at least. Now let's do something a little bit more interesting. I'm going to create, in front of my light while loop, I'm going to create a float. I'll call it angle. Let's just call it counter, how about that? That's going to initialize to 0.0f. And at every update, I'm going to say counter plus equals 0.1f. I don't know, that might be too much, that might be too little. It just depends. You might have to play around with this, because the way you have this set up now, this actually is going to vary how much it's translated, or affect how fast it's incrementing based on your processor speed. So, yeah, be a little bit careful with this. And before I update, in fact, yeah, just before all the shader stuff, I have to say transform.getPosition. And because I'm setting this, or because I'm getting by reference, what I can do is I can just say getPosition.x equals something like, I don't know, sine f of counter. And we can see what that does. So let's go ahead and build, and let's run. And hey, look at this. Notice it's moving back and forth. Just like that. It actually is a little bit fast in my opinion, so I'm going to slow that down to 0.01. And let's play around. Alright, cool. Now let's say transform.getRotation, .z. So that should be the axis around the screen. I'm going to set this to cosine f of counter. And now, okay, I think it is rotating just really slowly. So let's say cosine f of counter times 50. Oh. Okay, that's interesting. That's not quite what I expected. Huh. Well, it appears I may have a bug. One moment. And no, I don't have a bug. I'm actually... It's because I'm setting this to cosine, so the rotation on the z will only be between, well, 1 and -1, and that's not quite what I want. So let's just set it to counter, and not cosine f of counter. And... okay, it actually is also going really slowly, so let's multiply it by 50. Build and run. And hey, look at this! It's translating, and it's rotating around. So, there, we've got a translating and rotating triangle. And final thing to test out. Let's say transform dot... You know what, let's be a little bit more interesting with this. Let's say transform.getScale times equals cosine f of counter. There. And... invalid... oh. Right. There. And again, this only works because my getters are returning a reference. See? Right here? Reference. I just want to... whoops. Just want to make that clear. So let's build one last time, and run, and look at that. It's... and it's gone. Well, not quite what I had in mind. Oh, right, because I'm saying times equals. Okay. Never mind, that makes more sense. So let's try this again. Let's say transform dot... and in case you haven't noticed, I'm just playing at this point. So let's set the scale to... in fact, here, how about this? Let's have a float called sine counter, which is sine f of counter. Let's have some other float, cosine counter, which is going to be cosine f of counter. There. Just so I don't need to redo the calculations all over the place. So let's say set scale to a GLM vec3 of cosine counter, cosine counter, cosine counter. There. No. That's interesting. I'm pretty sure it takes in a GLM vec3. I forgot to make it a const reference to it for some reason. Okay. Well, that's my fault. I went for the getters and setters too quickly. I'm sorry. Let's try again. Okay. And now scaling should work okay. Yeah, there we go. So we've got a translating, rotating, and scaling triangle, all done with the power of matrices. Nice, efficient, and it's a little bit less intuitive than the way of just manually updating all the vertices in the mesh, but this is faster, it's more generic, and it scales a lot nicer when you have more geometry as well. So there you go. Hope you enjoyed, I hope you learned, and in the next video, what we're going to be doing is we're going to take a look at cameras, where rather than just moving our mesh around, let's see if we can move our camera around, make us fly all over the world and see different things. So thank you, hope you enjoyed, hope you learned, and I'll see you in the next video.